Okay, so another language aside here, now talking about language syntax of TL Verilog specifically, not Verilog. A lot of people always ask why I'm using AA instead of just A, and the reason for that is the naming syntax in TL Verilog. So TL Verilog uses fairly strict naming semantics for identifiers, like the pipe signals, they would be called. So a pipe signal starts, as every identifier does, with a symbol prefix, in this case a $sign, and then it's comprised of tokens, pipe and signal, and those tokens are delimited, in this case by an underscore. So these identifiers can have basically three different styles for the delimitation or the casing. So there's the lowercase syntax that's used for pipe signals, and that has underscore delimitation. There's camel case, or strictly speaking this would be called Pascal's case, because every token starts with an uppercase, even the first one. And in TL Verilog, when you're using camel case delimitation, instead of being a pipe signal, it's a state signal. I don't think we're even going to talk about state signals in this workshop, but nonetheless, just to understand syntax restrictions. And then there's also an uppercase, which I also don't think we're talking about, but that's all uppercase characters with an underscore delimitation. So the main message is, when you're declaring pipe signals, all lowercase, underscore for delimitation. You can have numbers in tokens, but always at the end of the token. So this base 64 is fine, but you can't have a number by itself. You can't start the identifier with a number. There are other types of identifiers that are purely numeric, and we'll see that this would be a head by one operator, and you saw that in the earlier example with the counter and with the Fibonacci series. All right, just mentioning Fibonacci series. Let's look at Fibonacci series now in a pipeline. So just taking the circuit that we had, putting that in the context of a pipeline, and not bothering to draw the flip-flops. Right, so essentially the difference here in the code is that I've explicitly given it a pipeline and explicitly put the logic into a pipe stage. So all of the logic in this example is in stage 1. The rest of it is just flops, which are, in a timing abstract sense, not logic. Okay, and this is absolutely identical to what we did before. It's just that before we weren't explicit about the pipeline. Everything in TL Verilog is in a pipeline. So even though we weren't explicit about the pipeline, the logic existed in a default pipeline in the default stage 0 of that default pipeline. All right, so now I'm going to give you guys a chance to code up some logic in a pipeline. And this circuit isn't anywhere near as complex as it looks when you're coding this in TL Verilog, where you're focused only on the logic expressions and the timing kind of takes care of itself. So let me set the stage for this example. This would be logic that would be accompanying other logic. So maybe you've got some sort of a computation going on in a pipeline, similar to what we did with Pythagoras' theorem. But this one's a deeper computation. It's over 6 cycles. And there are various conditions that could happen as you're computing the number. So the conditions that we have here are you've got bad input or an illegal operation that you're trying to perform. In stage 3, there might be an overflow condition. And in stage 6, you might detect a divide by 0 in the computation that you're performing. So these conditions are made up. It's not for any particular computation. But the circuit that you're looking at is simply taking these 4 different error conditions in this pipeline and aggregating them to result in a single error indication. And that error indication would be in stage 6 here, error 3. So your logic is simply taking these 4 different input conditions and ORing them together, right? So in the end, if any of these conditions assert, you need to assert this error 3 signal. Okay, so the blue circles are just ORs, and the red circles you are assuming to be inputs, and you can code up your logic to consume these, just assuming they exist. Maker chip will report that you're consuming a signal that's not assigned. It's a warning. You'll still get a circuit out of it, and Maker chip will just make up values for that for each of those inputs, and then you can look at your waveform and confirm the behavior. Okay, so again, you can pause the video, take your time with that example, and come back when you're all done.